My dear students, let me welcome you all to a new edition of physics. In this edition, we'll try to solve the problems on chapter 4, problems on AC circuits. The problems will be of gradual difficulty. Also, we'll try to revise the first 3 chapters. You will be encountered with miscellaneous questions, so stay with us. Problems on an AC circuits. First problem, a tuning circuit consists of 14 picofarad capacitor and the inductance of its coil is 5 millihenry. So capacity is given 14 picofarad. Pico is multiplied by 10 to the power of negative 12. Inductance 5 millihenry. Inductance is equal to 5 millihenry. Milli is converted into Henry. It is multiplied by 10 power negative 3. So once again, a tuning circuit consists of 14 picofarad capacitor and the inductance of its coil is 5 millihenry. Receives a wireless wave of frequency 600 kilohertz. If the coil is replaced by another coil of inductance 15 millihenry and capacity of its capacitor is increased by 28 picofarad, calculate the frequency of the new wave that can be received. So the capacity, the initial capacity C1 is equal to 14 times 10 to the power of negative 12 farad, and the second is equal to 14 times 10 power negative 12 plus 28 times 10 power, negative 12. It is 42 times 10 to the power of negative 12. First inductance 5 times 10 to the power of negative 3 Henry. And the second 15 times 10 to the power of negative 3 Henry. And now we can say F1 over F2 is equal to square root L2 C2 over L1 C1. So 600 over F2 is equal to, square root 15 times 10 power negative 3 times 42 times 10 power negative 12 over 15 times 10 to the power of negative 3 times 14 times 10 to the power of negative 12. So the second frequency is equal to 200 kilohertz. It is equal to 200 kilohertz. Okay. Another problem. We want you to find the readings on the voltmeters in the circuit shown in front of you. Okay, we want you to, find V1, V2, V3, and V4. What we've got here, we've got an AC circuit. Omega is given, to be equal to 314.28 rad per second. We've got a capacitor. Capacity of the capacitor is equal to 1.59 times 10 to the power of negative 4 farad. Inductance of the coil 63.66 millihenry. And ohmic resistor is 50 ohm. We want you to calculate V1, voltage across the ohmic resistor, V2, voltage across the inductor, V3, voltage across the capacitor, and V4, voltage across both inductor and capacitor. First of all, omega L is equal to XL, or XL is equal to omega L. So it is equal to, omega is given 314.28 times inductance, 63.66 milli should be converted, so multiplied by 10 power negative 3. In this way, we managed to obtain the inductive reactance. It is 20 ohm. XC equals 1 over omega C. It is 1 over 314.28, 1.59 times 10 to the power of negative 4. So it is equal to 20. And XL is equal to XC. This means that we've got resonance state because XL is equal to XC. And in this case, particular case, VR will be equal to V total. Okay, because we are in resonance state. And it is equal to, yes, the current times 50, so it is 100 voltage. And V2 equals I, V2 is the voltage across the inductor, it is IXL, so 2 times 20, it is 40. V3, voltage across the capacitor, they are the same, so 2 times 20, it is 40. Voltage across both of them, it is the difference. It is 40 minus 40, it is 0. Calculate the potential difference across each element of the circuit and the power consumed in the circuit. The circuit will be shown in front of you right now. It contains 200 volt effective value, 60 hertz the frequency, resistor of ohmic resistor 44, a coil of inductive reactance 90, and it has a resistance 36, a capacitor of reactance 30 ohm. So we need to calculate first of all the impedance. Z equals, yes, square root our total squared. Our total because we've got two resistances, one of the resistor and the other of the coil, plus XL minus XC all squared. So Z equals square root 80 squared, 80 which is the sum of 44 and 36, plus 90 minus 30 all squared. So Z will be square root 80 squared plus 60 squared, it is 100 ohm. Current is equal to the voltage over the impedance. It is 200 over 100, it is 2 amperes. Volt across the resistor, IR, so 2 times 44, it is 88 volt. Voltage across the capacitor, IXC, so 2 times 30, it is 60 volt. And your attention please, voltage across the coil will be IZ coil. So it is equal to 2 square root 90 squared plus 36 squared, because the coil has an ohmic resistor. So it is 193.86 voltage. And now power is, yes, is given by the expression I squared R total. So it is 4 times 80, it is 320 watt. And now we've got questions. First of all, give reason for. In the hot wire emitter, a wire of platinum iridium is used. Why platinum iridium in particular? The platinum iridium alloy has high coefficient of expansion, so it shows considerable expansion when a current passes through it. Another give reason. The scale of the hot wire emitter is not uniform. Scale of the hot wire emitter is not, yes, equally divided. It's not uniform. Why? The function of the hot wire emitter depends on the thermal effect of the electric current. Thermal effect of the electric current is determined from the relation I squared R. So the flexion of the pointer denoted by theta is directly proportional to the average value of the square of the alternating current. Theta is proportional to I squared. That's why the scale is not uniform. Another give reason, the hot wire emitter can measure both AC current and DC current. The function of the hot wire emitter depends on thermal effect of the electric current. and AC and DC have thermal effects, so they can be measured by the hot wire emitter. Another good reason, the hot wire emitter is provided with an adjustment screw to adjust the pointer to 0 scale. As a matter of fact, the resistance wire, the wire made of platinum iridium, is affected by changes of the atmospheric temperature. So its pointer moves away from the 0 scale, and hence it requires adjustment before using it. Another good reason, the resistance wire of the hot wire emitter is stretched over a plate made of a material that has the same coefficient of expansion as the wire. Why doing so? To eliminate, yes, to eliminate the effect of the atmospheric temperature. Atmospheric temperature is the temperature of the surroundings. In this way, the wire is kept taut as the plate will expand by the same amount as the wire. And now we want to make a comparison between moving coil galvanometer and hot wire emitter. Idea of the galvanometer, yes, it is based on magnetic torque or magnetic effect of the electric current. And what about the hot wire emitter? Yes, thank you very much. It is based on thermal effect of the electric current. So moving coil galvanometer based on magnetic effect or magnetic torque, but hot wire emitter based on thermal effect. Moving coil galvanometer only measures DC currents, but hot wire emitter measures effective value of an AC currents, and it measures DC currents. Scale of the moving coil galvanometer is uniform because theta is proportional to I, but scale of the hot wire emitter is not uniform because theta is proportional to I squared. The pointer of the device stops when measuring a current, okay, and the current is connected to the device. The pointer of the device stops moving when the electromagnetic couple is balanced by the mechanical couple. If you remember, mechanical couple is produced by hair springs. And what about the hot wire emitter? The pointer stops moving when the resistance wire reaches the temperature at which heat produced in the wire due to the flow of current equals the heat lost by convection. Moving coil galvanometer has high sensitivity. Hot wire emitter has much lower sensitivity. Talking about disadvantages of the moving coil galvanometer, first of all, as time elapses, the hair springs become inactive. They become slacken away. They slacken away, and the magnet loses, yes, some of its strength. So the device requires recalibration from time to time. This is one disadvantage. Also, it only measures direct currents. It cannot be used for measuring alternating currents. And what about, yes, disadvantages of the hot wire emitter? First of all, its sensitivity is small. It is affected by atmospheric temperature, and it takes time. The pointer takes longer time to measure the current, and it takes longer time to return to zero when the current is disconnected. Another type of questions, what happens when in front of you we've got a circuit that contains 6-volt battery, switch, electromagnet. Across the ends of this electromagnet we've got neon lamp. What happens when the switch is opened? Okay, and you have to justify your answer, account for your answer. Actually, the lamp momentarily flashes due to the high forward EMF induced by self-induction. What happens when the two metallic rings in an AC dynamo are replaced with a split cylinder commutator? Okay, the current becomes unidirectional, but still varying current. It changes from 0 to maximum, but it has just one direction. And now we've got a circuit. What happens when the value of R1 is decreased with respect to the readings on the 2 voltmeters? We've got 2 voltmeters here. A voltmeter V1 across the cell, and it, yes, reads terminal voltage. And V2 reads the voltage across R2. Okay, we'll take it one by one. V1 decreases, but V2 increases. We'll explain this. Decreasing the value of the variable resistance. If R1 is decreased, total resistance of the whole circuit decreases, current increases, and internal voltage increases, so external voltage, which is V1, decreases. So decreasing the value of the variable resistance decreases the total resistance of the circuit. And what happens to the current? Current increases. So the current passing through the battery increases. And this increases the internal voltage. And this causes the internal voltage to increase. And when internal voltage increases, terminal voltage decreases. So V1 decreases. And what about V2? V2 is obtained by the product of I multiplied by R2. R2 is constant, so it depends on current. What happened to the current? Okay, so V2 increases because the current is increased. V2 is proportional to the current. Another type of questions: when does each of the following quantities equal 0? When does the torque acting on a coil carrying an electric current and placed in a uniform magnetic field equal 0? This happens in the vertical position. Torque equals 0 in the vertical position. When the plane of the coil is perpendicular to the magnetic field. Torque is given from the expression BIA n cosine theta. Torque equals 0 when theta equals 90. Theta is the angle between plane of coil and magnetic field. Okay? This happens in the vertical position. Vertical position, plane of coil makes an angle 90 with the field, and cosine 90 equals 0. That's why it is 0. When does the EMF induced in a wire moving in a uniform magnetic field equal 0? We've got a wire that moves, okay, in a magnetic field, but no EMF is induced. Okay, so the wire must be moved parallel to the field. Okay, when the wire is moved parallel to the field. EMF instantaneous induced in the wire is given from the expression BLV sine theta. B is magnetic flux density. L is the length of the wire, V is linear velocity, theta is the angle between direction of motion and magnetic field. So EMF is equal to 0 when theta is 0. Theta, as I said, is the angle between the field and direction of motion of the wire. When does the force of a magnetic field on a current carrying wire is 0? This happens when the wire is placed parallel to the field. Let me explain it. We've got a wire and a current is sent into the wire, and the wire is placed in a magnetic field, but no force acts on it. Okay, this happens when the wire is placed parallel to the field. Force is given from the expression BIL sine theta. Once again, the force will be 0 when theta equals 0. Thank you very much. Okay. When does the instantaneous EMF induced in a coil rotating in a magnetic field equal 0? Instantaneous EMF induced equals 0 in the vertical position where the plane of the coil is perpendicular to the magnetic field. Sides moves parallel to the flux lines, no cutting, so EMF is equal to 0. Okay, EMF instantaneous is given from the expression EMF maximum cosine alpha. So instantaneous EMF will be equal to 0 when alpha is 90. Okay. Alpha is the angle between the plane of coil and magnetic field. And we've got another situation here. Current flows through the primary coil, although it is connected. Okay, it asks, we've got, yes, a primary coil of a transformer connected to the supply, but no current flows through it. Okay, we want your explanation. Thank you very much. This happens when the secondary coil is unloaded. That's to say the secondary circuit is open. And on this particular situation, no current would flow in the primary circuit, even if it is connected to the mains. And now we've got a problem. The figure shows two long straight wires that carry the same current. It is denoted by I1, but in opposite direction. It is quite shown in front of you. And we've got a loop that carries current I2. So I1 is the current that passes through each wire. Okay, the two wires carry the same current but in opposite direction. And we've got a circular loop that carries current I2 in clockwise manner. And the problem says when a compass is placed at the center of the circular loop, it shows no deflection. And we want you to compare I1 to I2. At the center, okay, the two wires, the two fields of the wire, okay, since they carry currents in opposite direction, between the two wires will have the same direction. So 2B wire will be equal and opposite, yes, the magnetic field of the circular coil. So we can say 2 times permeability I1 over 2 pi r is equal to mu Ni2 over 2r, and we've got a loop, so number of turns is equal to 1. Permeability will be cancelled out, and 2 also, and r will be cancelled out, so we can say 2I1 over pi is equal to I2, and remember n is equal to 1. So in this way we can compare I1 to I2. It is pi over 2. Another interesting problem, we've got two wires that carry currents in the same direction, and this means field between the two wires are in opposite direction. And we've got a circular coil that carries current in, yes, anti-clockwise manner. You pay attention to the distances given. Okay, distance between the two wires are 40 centimeters. So the two wires are 40 centimeters apart. Okay. The figure shows two long current carrying straight wires. The two wires are 40 centimeters apart. The first wire carries a current of 15 ampere and the other carries a current of 20 ampere. A circular coil of radius 2 pi centimeter is placed between the wires such that they have the same plane. If the current flowing in the circular coil is 0.05 ampere and the magnetic flux density at its center is 0, calculate the number of turns on the coil. So we can say B circular plus B wire B is equal and opposite the field produced by wire A. So mu O 0.05 over 2 times 2 pi times 10 to the power of negative 2 plus mu 15 over 2 pi plus over 2 pi times 0.2 is equal to mu 20 over 2 pi times 0.2 mu 20 over 2 pi times 0.2 minus mu 15 over 2 pi times 0.2 is equal to mu 0.05n, and is the number of turns we want to calculate, over 2 times 2 pi times 10 to the power of negative 2. Okay, mu will be cancelled out, and in this way number of turns, yes, was 10 turns. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.